All right, so now here's what we're going to do. All right, we're going to kind of combine what we all did. All right, so I'm going to first write my dimensions that I started with in this table right here. So I did a 4x4 square. My dimensions were 4x12x20. So my volume was 960. All right. Now, let's just kind of go down what size boxes y'all made. So did anyone do a 1x1? Raise your hand if you did 1x1. So you cut out a 1x1 square. No one? All right. Who did a 2x2? All right. So Jacob, what were your dimensions? Okay. Fatima, what were your dimensions? Guys, hush. Shh. And what was your volume? 768. All right. So doesn't beat mine. So far mine is kind of winning. All right. Bigger volume. All right. Who did anyone do a 3x3? All right. So let's go Leighton first. What was your dimensions? So 3x14x22. All right. Maria, what was your volume? 924. Is that what you guys also got? Okay, good. All right. Did anyone do? Yeah, you need to write down this table. All right. So this table you need to be writing down. Now, did anyone do a 5x5? All right. All right. So let's go, Brayden. What were your dimensions? Good. Paula, what was your volume? 900. Good. All right. Anyone do a 6x6? All right, got some 6x6s. So let's go with Celeste. What was your dimensions? Good. Tobias, what was your volume? It was what? 768. Is that what everyone else got? Who did a 6x6? Good. Did anyone do a 7x7? All right, Carter. So what were your dimensions? So it was 7 by what? 6x14. And what was your volume? 568. Did anyone do an 8x8? Did anyone do a 9x9? All right. So Jason, what were your dimensions? 9x4x11. What was your volume? 396. All right. Now, here's my question to y'all. Is it possible to do a 10x10? No. Why? It's a 20 width, so if you do a 10x10, then you just have a rectangle again because you cut out the width. All right. Because what you would do is you cut out these edges completely. All right. So, now, based off of this, what did we find the largest volume to be? 4x4. All right, so mine, I didn't do that on purpose. Mine just happened to be the biggest volume. All right. I didn't test it beforehand. Okay. I didn't. Seriously. Positive. You can ask all my other kids. They've done 18x24 papers. So different. So ours was a 20x28. They've done 18x24. So different dimensions, different volumes. All right. So Mine was the greatest volume. So the largest square, whole number that can be cut from a corner, happened to be a 4x4 square. And the dimensions were 4 by 12 by 20. Now, if I did not have you physically cut out the squares, how do you think you would figure out what your dimensions were? So think about it logically. What do we start with? What size rectangle do we start? We started with a 20 by 28. All right. Now, if we use mine as an example, guys, put the scissors up. So I cut out a 4x4 square, which gave me a width of 12 and a length of 20. All right. So in reality, my width was originally 20, now it was 12. So how much did I subtract? 8. So I subtracted 8 from the original. How much did I subtract from the original here? 8. Now, why is that? 4 plus 4 is 8. And we did how many boxes on each side of the rectangle that we cut out? We cut out 4 corners, but on one side of the rectangle, how many were cut out? 2. So 4 units here, 4 units here. So that's what we did. So in other words, whatever length dash width your square was, double it and subtract from original length and width. So let's do the size squares that we didn't have anyone do. So we didn't have anyone do a 1 by 1. So let's say we did 1 by 1 square. What do you think my new dimensions would be? So we know the height's going to be 1. So it would be 18 for the width, because if we do 1 times 2, that's 2. 20 minus 2 is 18. And then what's the length? 26. Good. So someone go ahead and calculate that volume for me. 468. All right. We also didn't do a 8 by 8. So 8 by 8. All right. We know our height would be 8. What would my width be? So 8 plus 8 is, oh Lord, 8 times 2 is 16. Subtract that from 20, you get 4. What would your length be? 12. So 28 minus 28 minus 16. It's 12. All right. Now, someone go ahead and do that calculation for me. It's what? 384. Good. All right. So now let's look at all of our different volumes. So what happened if I cut a bigger square than a 4x4? The volume starts getting smaller. So the volume starts getting smaller. Now, we already cut out the largest square, which was a 9 by 9. And did it result in the largest volume? No. So the 9 by 9 did not result with highest volume. All right. So when we compared our results again, the 4x4 square created our largest volume. Now, this was kind of a exploratory thing. So what we're going to do now is I'm going to give you guys your 3-minute break. Now, what I want you to do on your way out, I want you to put up your scissors if you haven't already and throw away your trash. You can keep your box if you want, or you can trash it. All right, it's up to you. Yeah. Make sure you're quiet in the hallways. So put up your scissors. You can keep your box if you want to, or you can throw it away. Just make sure your trash. Make sure it's my trash can.
Yeah. I told you. No. I'll give it some down. Yeah. I'm gonna. You get show something. Okay. I wouldn't actually go. I spent less time on it. I was kind of not. Yeah. I didn't do anything. What is that with you little boys?
They always throw you on.
That's fine. I don't know what you break. You would never do that.
All right. All right, guys. Go ahead and have a seat. We're going to now talk about the actual notes. All right. So look at the next page of your packet. So open box volume is actually a lesson. Okay. So the reason we did that exploratory thing first, so you can kind of wrap your head around what I'm talking about. Okay. So basically, if you are given any size rectangle, you should be able to figure out what size open box you can make and the maximized volume. All right, and what dimensions would give you the maximum volume. Okay, so first off, let's actually talk about how we would figure it out algebraically. How we would set up an equation to figure out our dimensions of our box without actually having to cut it. So we're going to take things that we did with the exploratory stuff, so what we did concretely, and we're going to apply it. So first off, let's say that we had an x by x. So we have some length here and some width here of a rectangle. All right. So this is our original length. This is our original width. Now, let's say that we cut an x by x square. So we don't know exactly for sure how big of a square. We just know it's an x by x square. And that's for all of these. So this is an x by x square, x by x square, x by x square. So let's think about this carefully. Your height was typically what? So like when we did our activity and you cut your square out, what was typically your height of your box? So in other words, right here. The same as what? The same as your original square. So what if we had cut out an x by x square, what do you think my height's going to be? X. There you go. Now, to find the length, all right? So what do we do to find the length? And we kind of came up with it up top after the fact. But what did I say you could do to find the length of the box without actually having to count it? So it'd be the original, and then you would subtract double your height. All right. So we would take our original length and we would subtract 2x from it, which is our height. So twice the height, or in this case, 2x. And that would give us our new length. And we would do the exact same thing with the width. So we take our original width, we would double our height, and subtract that from the width. Because remember, so like for example, with my 4x4 box, I took 4 units away on this side, 4 units away on this side. So if this was 28, I would subtract 8. This should be 24, which it was. Same thing over here. 4 boxes over here, 4 boxes over here. I subtracted 8. So from 20, that should be 12 across the top, which it was. All right. So this right here is your general formula for an open box. All right. So if I ever ask you an open box question, that's how you should set it up. You take your original length and your original width and you plug it in. All right. And why is this important? Because I'm going to show you how to actually find the maximum volume. So first off, just to do some labeling here, your new length would be length minus 2x. Your new width would be width minus 2x. Now, I want everyone right now to take out your Chromebook and go to Desmos. Huh? No, I want everyone to have it in front of them. So I'm going to set the scene so Desmos should automatically open up for you. All right. So everyone got Desmos up. All right, come on. It should automatically open up for you. Put in Desmos.com. All right, everyone got it, Desmos? All right, so before we do anything with Desmos, let's first come up with a formula that would represent what we just did previously. All right, so in other words, we're going to replace L and W with our original length and width of our grid that we had. Okay, so what was my original length of my rectangle? In the activity that we did, what was the original length? 28. So this would be x times 28 minus 2x. What was the length of the width? 20. So I'm going to put 20 minus 2x. So this formula represents what we, that's a parenthesis. So that represents what we did in the activity. And we're going to use this formula to answer some questions. So we're going to see if we do this stuff algebraically, if we will get the same answer that we came up with when we actually did the activity. All right. Now, we're going to keep this function in factored form, and I want you to graph it in your graphing calculator. So I want you guys to put this function right here, so the one I just wrote down, into Desmos and type it exactly like that. You don't need to put the v or anything. Just type the x times 28 minus 2x times 20 minus 2x. And I'm going to do the same. So I'm going to type in x times 28 minus 2x times 20 minus 2x. You may need to zoom out to see the full picture. Okay. I'll leave the x-axis as is. All right, so what I did is I went ahead and constrained my window in Desmos. So what you want to do is go to this little wrench, and you're going to type in, I would type in from 1 to 9 for x, because that's how big of a box we could do, from 1 square to 9 squares. Just trust me. So just type in 1 to 9. Go to the wrench key. See where it says x-axis? 1 on this side, 9 on the other side. So I'm going to type in 1 here, 9 here. I'm about to tell you. All right. Did everyone constrain their x-axis? Now the y-axis, let's just go type in, let's say, negative 4,000 to negative, no, let's go 1,000, because it's not going to get bigger than that. So let's go to negative 1,000 to 1,000. Just so we get a decent idea of what the picture looks like. And once you do that, you can click out of your wrench. Now, you may still want to kind of manipulate it a little bit, but that's okay. So I kind of shrunk it just a little bit. But the window that I gave you should be that way. Yes? Huh? Okay, you can't hit the home button. You gotta hit the wrench key and get rid of it. So hit the home button, it's gonna reset to the original. All right. Now, here's my question. Why do you think I did your window from 1 to 9? What does X represent? What part of the side? So it's the size of the square. It was the height. All right. So remember, the biggest size of a square that we could make was a 9 by 9. The smallest size we could make was a 1. So that's why I did 1 to 9. All right. And then the Y's, I just picked random numbers that just help us see it. So since I knew it was going to get big, I did 1,000 to negative 1,000. All right. Now, next thing I want you guys to do, I want you to find the relative maximum. Now, what would a relative maximum look like? So think quadratic. When you had a maximum for a quadratic, so a parabola, the maximum was like the top of the mountain. All right. So in other words, Desmos should already have it highlighted for you. All right. So, and we're going to just round this a little bit. So let's round it to 2 decimal places. So our maximum value was 3.83, was it? Guys, please stop talking. Yeah. To, it was 961 point what? 32. Now, what does the x value of the point mean? What does that represent? So in our equation, so in this equation right here, what was the x? What did the x value represent? The height. So this represents our height or the size of the square to cut out. And this over here represents our what? The volume. Because our output over here is V, so that's the volume. So this is actually the max volume. So if we cut out, so if we cut it out, the technically this volume actually did beat mine. Mine was 960. So let's say we had a ruler and we did a 3.83 size piece of square. So if we did a 3.83 by a 3.83 piece of square. Oops, wrote that in the wrong spot. Goes for B. So we did a 3.83 by a 3.83 square. Our maximum volume for that entire piece of paper would be 961.32 units cubed. All right. Now, this is how you find maximum volume from any size paper. All right. So you would take the original length and width, put it in that formula, graph it in Desmos, the entire formula in Desmos, find the maximum. And that's your, whatever the y value is, that's your maximum height. Whatever the x value is, that's what size square you're cutting out. Does that make sense to everyone? All right, now let's go back to our graph. All right, so let's go back to Desmos. Now I'm going to zoom out a little bit so I can see all my intercepts. The next thing we're going to do is we're going to find all of the x-intercepts. So click on all of the x-intercepts. So it should be 0, 10, and 14. We're now going to discuss what we think those mean. All right. So first off, 0, 0. So think about what the x value means. If I start with 0, 0, what would that mean in terms of this situation? So if my height was 0, the size of the square I took out was 0, what is it really? Isn't it just my whole paper? So that's what it represents. It represents my uncut paper. Now, the other x-intercept was 10. So, think about this carefully. If that represents the size of a box you can cut out, all right, could we cut out a 10 by 10 box on the paper and still make a box? No. So a 10 represents the size square we cannot cut out. So another way to put that is that it is the max square. All right. So anything less than 10 is a square that we can still make a box from. So it could be a 9.99999 square. We can still make a box. It just be this tiny sliver of a box. All right. But if we do a 10, one of our sides just completely disappears. All right. Now, the last one that we had was 14. Now, let's think about this logically. So, how do we know that we couldn't cut more than a 10 by 10 square? Why? Say it again. I'm sorry, I just can't hear you. We would get another rectangle, but how do we know? Right, because what's 2 times 10? 20. Isn't one of our lengths 20? Yes. All right. So what about 14? What would happen? So it would cancel out the 28 because 2 times 14 is 28. All right. But we can't cut a bigger box than a 10 by 10 anyway. So in other words, in context of the meaning, it has no meaning. So you can say that 28 is equal to 2 times 14. All right. But the main reason is that we don't use it. So in context of the problem, it's irrelevant. Because we know the biggest size square that we can cut out is anything less than 10. Now, what did I say the x represents in this situation? The x equals the height. So x represents the height. So what would be an appropriate domain for this situation? So in other words, what is the lowest x value that we can have to the highest x value? Okay, so let's talk about this for a second. So if we look back at Desmos, if we're looking at specifically the x-intercepts that we like, what part of my graph are we actually using to represent the volume given any height? What part of this graph is between what two numbers? 0 and 10. So between here and here, this represents any volume given any size square that we cut out. All right, so we can cut out a 5.5 square. We can cut out a 6 1/4 square. All right, and that volume would show up in here. So, how do you think I would write a reasonable domain? So remember, domain's what? What value is domain? X. All right. So essentially, we're going to say that it's between what two numbers? 0 and 10. Now, is it going to be defined at those numbers? So in other words, are we going to actually get a volume if we have a height of 0 or a height of 10? No. Because if I cut out 10, it's not anything I can make a box out of. It's just another rectangle. If I cut out 0, we're just left with our original rectangle. So that means we either have to write it with parentheses, so we can say parentheses 0, 10, or you can write it as an inequality where 0 is less than x, which is less than 10. All that means is that it has to be between 0 and 10. All right. Now, what about an appropriate range? So what does range mean? Range is your y values. So let's look back at our graph. All right. What is our lowest possible volume? Or in other words, what volume would be like the closest to the lowest possible volume that we can imagine? 0. So right here is where our lowest possible volume is. It's not going to actually hit 0 because then that's not a volume. But let's say our volume was like 0.00000000001. All right, which that would be like infinitesimally impossible for us to cut out, but maybe a robot can do it. All right. So that's our lower bound. What will be our highest? What was our highest volume? 961 point something. So whatever this max is. All right, and that's exactly how we're going to write our range. Now, would it actually hit our max volume? So in other words, what would be defined there? So is it possible for us to hit our max volume? Yes, very possible. What about the minimum? So 0. Is it possible to hit 0? No. So the way we would write this is, first off, y represents the max volume, or not max volume, just volume. So the appropriate domain would be from 0 to 961 point, what do we round it to? 32. And we will put a bracket on the end of the max volume. So we'll put a 0 with a parenthesis because it doesn't quite hit 0 because we still want it to be a feasible volume. But then we put a bracket on the max volume because it taps out there. It doesn't go past it. The other way you can write it is 0 is less than x, or not x, y, which is less than or equal to 961.32. So does everyone understand how I got those domains and range? So when they ask you to find an appropriate domain or an appropriate range, they're talking about in context of the problem. What would logically make sense in context of the problem? Because if we just look at the graph, so if we just look at the original graph as a whole, the domain of this graph, just this graph in general, is negative infinity to positive infinity. It's all real numbers. The range is also all real numbers. All right. But is it possible to have a negative height? No. Is it possible to have a negative volume? No. So it doesn't make sense in context of the problem. All right. That's what appropriate domain and range mean. All right. Does that make sense to everyone? All right. So this just kind of restates what we already found in terms of the problem. A generalized formula would be x length minus 2x width minus 2x. We already stated that. We're just stating it again. I kind of jumped the gun, but that's okay. So that's your general formula for any open box problem. All right, so let's do some examples. So what we're going to do like 1 or 2 of these. we're going to say that we were just given a piece of paper, no grid. All right, and they just asked us to use a ruler and cut out a certain size square on each side, just like we did with our practice earlier. All right, so we are going to, these are the steps right here. We write the polynomial equation using the formula that we just came up with, so x times length minus 2x times width minus 2x. We put it in our calculator and find the max. We're going to draw a quick sketch of the graph. We record the x value that we're going to cut. We're going to state the actual maximum volume, and then we're going to give an appropriate domain and range. All right. So first off, my paper size. It's just a standard piece of printing paper. So it's an 8x5, it's an 8.5 by 11 inches. So in other words, it's literally just a standard piece of white paper. All right. So let's put it into our formula. So what would my formula look like? So the volume would equal what? So you're just going to take those two dimensions and plug it into this formula up here for length and width. So what would it be?
B equals space.
X times 8.5 minus 2x times. Good. So guys, all you're doing is taking the formula we came up with. So volume is equal to x times length minus 2x times width minus 2x. And just plugging in what they gave you for the length and the width. That's all you gotta do. You just gotta plug in two little numbers. That's it. The rest of it you write verbatim. All right. Now, go ahead, put that in your calculator. So go ahead and type that into Desmos. So in reality, you really only need to change those two numbers. You don't have to like retype an entire thing. So this would be 8.5. This would be 11. And then I'm going to zoom in a little bit just so I can see what's going on. So you may want to change your window, or you can hit home to resize it and then zoom in and out. So I got a graph that looks like this. All right. We're going to draw a quick sketch of the graph. All right. So your graph looks something like this. So it goes up, comes back down, goes down a little bit, and then goes up to infinity. So this is what our graph looks like. The part of the graph we care about is from the origin to our first x-intercept. All right. So this section right here, that's the only part of this graph that we care about in terms of the problem. Now, find the max point on that graph in Desmos. What is it? So what's this max point right here? What's the point? And if you have to round it, round to the nearest hundredth, so 2 decimal places. So guys, all you gotta do in Desmos is it already marks it for you. You just gotta click on that point. So it'd be 1.59 and then 66.2. So it'd be 1.59 and then 66.18. Or was it 1.5? Yeah, it was 1.5. My bad. Shh. Guys, please stop. So the graph is part B. Guys, please stop your mess. All right, now, what is my maximum volume? So what part of my maximum point is my volume? 66.15 is my maximum volume. So it'd be 66.15 inches cubed. Oops, I recorded that in the wrong spot. That's D. What size square should I cut? $1.59. So we should cut a 1.9 inch by a 1.9 inch square. So given that, let's figure out appropriate domain and range. So first off, we also need to find out what this x-intercept is right here. All right, so not the x-intercept that's 0, but the other one. So if I zoom in a little bit, it'll be this first one right here. So what is that? 4.25. So this x-intercept right here is 4.250. And then this one's just 0, 0. So domain. Look at the section that I highlighted. What values will my domain be between? 0 to 4.25. Now, would I use brackets or parentheses? Parentheses for both. So we write 0 to 4.25. What about range? So what is the two numbers as between? 0 and what? 0 and 66.15. Good. So, now, will we use a parenthesis or a bracket for 0? Does it actually hit 0? It's parenthesis. What about for the 66.15? Bracket or parenthesis? Bracket. Okay. Any questions on that? I want you guys to take a minute, try number 2 on your own. That'll be the last thing we do today. So try number 2 on your own. So it's the exact same process that we just did. You're just going to plug into the formula, put it in Desmos, find your max and your first x-intercept, do a quick graph, and then use that to answer the questions. So guys, everyone should be trying this problem. Uh-huh. Didn't you just go?
Yes.
What's the break for then? 3 minutes. You can use the bathroom in 3 minutes. Go. Guys, you do realize that all you're doing is make me want to do a seating chart, right?
Please do not.
Then stop screwing around and do what I ask you to do. Yeah, but I'm just doing it so you guys can check it. All right, I'll give you guys one more minute, and I'm going to have you guys check your answers.
How's your day going this weekend?
Fine.
Great, because I'm in it.
Bro, ain't nobody asked you. Why? You're just answering out of free will.
All right, thumbs up if you're ready. All right, looks like a majority, so we'll go ahead and move on. All right, so check your answers. So while you're checking, I'm just going to go over it. All right, so this should have been your formula. We had a 10 by 10 sheet of paper, so I just replaced 10 for the length, 10 for the width. I typed this exactly into Desmos. I got a graph that looks somewhat like this. So it bounced here at its x-intercepts, so there should have only been 2 x-intercepts. All right, so it went from 0 to 5. Your max should have been 1.67 and 74.07. All right, it's just a freaking number, y'all. All right, so your size box that'll give you your maximum volume is a 1.67 centimeter by 1.67 centimeter box. Your maximum volume is about 74.07 centimeters cubed. Your domain is between the 2 x-intercepts from 0 to 5. Remember parentheses because they don't actually hit that. And your range should be from 0 to your maximum volume. Remember the max volume has a bracket. The 0 has a parenthesis. Any questions on any of this? You guys feel pretty confident about this?
Yeah.
Not too bad? It's just a formula. I just would manipulate like this because like now you're manipulating. Well, you know you gotta put zero. All right, so here's what we're gonna do next. Even though we got about like 15-ish minutes left. So what we're gonna do next is there is a quizzes on this. It should already be assigned to you. You should pretty much be able to do at least part of it. All right. So go ahead and log on to quizzes. You're still gonna want Desmos open. I gotta change the scene, so hold up. All right, so you can go ahead and log on to quizzes. It's called 7.1 open boxes.